Hi, we are the 24-hour energy generation capstone group. I'm Charlie.
I'm May.
I'm Subi.
Melissa.
And I'm Nico.
So the foundational technology behind this project is Dr. Zhang's 24-hour energy harvesting device. It works using the sun as a heat source and soil as a heat sink. That thermal differential between the two creates electricity through a thermoelectric generator, or a TEG. And that TEG also works at night using the soil as now a heat source and the outer space as a heat sink. So the background, why this project exists, why it might make an impact. Well, the UN has established the goal of universal energy access by 2030. Currently, 860 million people are without access to energy, and the International Energy Agency has declared that decentralized solutions will be key in meeting those needs. So instead of power plants, think small solar panels, wind turbines, and our device. Over $40 billion in annual investment is required to meet these needs by 2030. So there's a lot of money going into this space. The market we've established really depends on what's novel about the technology, and that's that it generates 24-hour energy without the use of batteries. So batteries are really expensive, so we're thinking maybe our device can compete on cost. We thought about creating a small solar device, think of like a solar lantern. These are called Pico devices, but sales have been falling in that realm, so the market isn't really asking for it anymore. Instead, standalone residential energy systems have been emerging. So we want to create a proof of concept prototype for a 24-hour energy generating system that meets the needs of a residential house in a developing country.
So some key terms that we'd like to define are TEG, which is a thermoelectric generator, PV, which is a photovoltaic, so this refers to solar panels, and concentrated solar. So that is the process of using mirrors and lenses to concentrate sunlight into a small receiver.
So the prime goal of Capstone 1 is to create some objectives, your system specs. And we have done that with a set of assumptions. The biggest assumption is that we are optimizing this system for nighttime generation. And that is because the nighttime generation is the more novel and unique aspect of this technology. Given that, we are hoping to create 3 times the power density at night by increasing the delta T across the TEG. The professor said that this 2 to 3 times seems feasible for an efficiency gain. And we're also looking to increase our energy generation because our heat sink for the TEG has a much more constant temperature throughout the night. And so you'll see that later in the slides. And we're also estimating a 20% power density loss during the day because we're optimizing for nighttime. We've also created a basic access load profile, which basically describes what we imagine is your basic access to electricity, what products you would be using in a developing country. And our test product is only going to be 10% of this power output in size. So here's the load profile. It was created by taking 5 different appliances we imagined people would be using: clock, radio, LED light, chargers, fan, and a water pump. And then applying their wattages, the amounts that they would use, and the time of day that they would be used in, and this load profile that we came up with. On the next slide, you'll see that we use this load profile to create our demand. And the blue here is the demand. The negative axis shows anything that is going out of the power circuit, and the positive axis is anything that is going in. So on the positive axis, the combination of TEG power used and PV power used is exactly mirroring our demand. And then the green is any of the power that the TEG and the PV are producing that is not being used by the demand, that is then going to be stored as energy for nighttime generation, which I'll explain on the next slide. So this is our general system overview. This is the TEG combined with our load and our PV panel to create a microgrid to supply the load that we're trying to achieve. Our PV panel has been spec'd for 10 watts, and our TEG is approximately going to be 10 meters squared. So during the day, it's taking in, the PV is taking in solar energy to give power to the load, and then all the excess storage is going to go into a resistive heater in our water tank to increase the water tank temperature, which is where we get that delta T. And then at night, you can see that the PV isn't generating anything, but all of the power that the load is getting is from the TEG and the temperature differential that we've gained.
So one aspect of our design is this solar concentrator. And what that intends to do is heat up the water as much as possible to optimize the TEG for that nighttime power output. So in general, solar concentrators, a big balance is between acceptance angle and concentration. So for something like the sun, which moves around all day and all year, it's always in a different place, you want a wide acceptance angle because you can't rely on just one fixed spot. So that wide acceptance angle allows a lot of light to enter the solar concentrator throughout a variety of different times. But if you widen your acceptance angle, you decrease your concentration ratio. So that decreases your power intensity into the concentrated element. So what we'll need to do during the design phase is figure out the optimal balance between acceptance angle and concentration ratio. We also need to be aware of absorption and reflection losses. So you can see in this design concept, the sunlight passes through glazed glass in a couple different areas. At each one of those spots, there'll be some heat absorbed by the glass and some reflected away. So those are things we're going to need to consider during the design phase. And then lastly, like Melissa has mentioned with the solar PV, there needs to be an optimal tilt angle for this solar concentrator to direct it towards the sun based on what latitude this device will be operating at. So some sort of adjustable tilt system might be the solution here. And again, that will be figured out during the design phase.
So initially we were considering designing and creating our own TEG modules just to increase efficiency. However, we realized that this would be very time consuming and create a bulky product. So it's just easier and more time efficient to buy an off-the-shelf module. And they are relatively inexpensive for our purposes. The way that TEGs work is that they use semiconductors to create a voltage by having a temperature differential. So they are insulative in their nature, and they don't allow heat to transfer through. And that is how they create or detect the big difference between the heat source and the cool side. So once we realized we weren't going to create our own TEG, we started looking more into material properties for our heat source / heat sink, depending on whether it's daytime or nighttime. And after looking at lots of different materials and their properties, we realized that we want to optimize our system by choosing material that has low thermal conductivity and a high heat capacity in order to not heat up so much during the daytime and maintain that temperature differential throughout the day, but also retain heat throughout the night after it's absorbed throughout the day. So we've decided that the main material will be water, but we're also considering other materials to either incorporate into our testing or design, such as rubber, wet soil, like sandy soil or clay soil.
As Melissa previously mentioned, our system will include a tank, which will be located below the TEG, and it's going to be filled with water that has been heated by the sun during the day. To keep the water hot, we will use an insulated jacket around the tank so that the heat can only escape through the top part of the tank, which is where the TEG is placed. This will keep the temperature differential between the hot and the cold side of the TEG high throughout the night. And this will have a better power generation. Having said that, we looked at the most common insulators used in the market, such as EPS, fiberglass, and foam. We consider 5 criteria to determine which insulation will be more adequate for our purposes. We look at the R value of the material, which determines the thermal resistivity directly. And so the higher R value, the greater the resistivity, therefore the better insulation. We're also considering price, whether the material is flammable, since the tank will be placed in the environment, and whether the material is environmentally friendly. So by looking at the table, we are leaning towards fiberglass, which is the cheapest option with a reasonable R value, and EPS, which is slightly more expensive, but with a higher R value. We still need to conduct modeling with these different materials to determine the most optimal choice. In addition, we are also considering using fins in the tank to encourage heat transfer between the TEG and the water. However, we still need to run some calculations to determine if these fins will eventually have an impact or not. And we will do so during the design stage of the project.
So simply put, radiative cooling is the process by which a body loses heat by thermal radiation. And for this process, we are considering the use of different black body emitters that can be used to optimize the temperature differential between the TEG and outer space. And for daytime radiative cooling, we want to create a structure that reflects all the sunlight, but strongly emits between the between the 8 to 13 micron window. And as shown in the second figure, the silicon present in TEGs, they have great absorptivity rates, but they lack the emissivity and therefore are not very good radiative cooling material. And so we aim to use the application of photonics to help increase the performance of such an emitter. To do this, we will use a photonic crystal layer that introduces periodic air pockets in a specific geometrical formation. And this will allow the photonic crystal to behave as a visibly transparent black body and allow the emissivity to fall within the optimal range. In search of sustainable materials, we came across a type of silica called obsidian, which is naturally produced through the rapid cooling of silica-rich lava, and this prevents crystal structures from being formed. And this allows obsidian to have 1/10 of the heat capacity of igneous rock, and even if they conduct the same amount of heat, obsidian will heat up 10 times as fast, and therefore allows heat to easily pass through. Additionally, thermal design will be very important to prevent parasitic heat leakage from the water and also from the radiation. And so to do this, we're going to consider things such as a radiation shield and also the way we lay out the conductive pathways.
So some of the project challenges that we're anticipating are optimizing the specific components that we just talked about in order to make them as efficient as possible. And one of the issues that arise with this is solving the insulative TEG problem, which is the fact that the TEG is an insulator. Solar power doesn't necessarily transfer through that module and heat up the water. So we're trying to think about different configurations in order to take advantage of solar energy. And as Nico mentioned earlier, we want to design to minimize radiative losses. And since testing and getting numbers for our power generation will validate the design, we need to be aware of designing for testability.
For the project plan, we identified seven milestones, as you can see from the slide. Background research, design requirements, modeling, design, development, testing, and validation. We already completed the first two milestones, background research and design requirements during this summer. We plan on spending the first 4 weeks of the fall semester to designing. We will also be writing the test plan simultaneously, which will include testing goals and procedures on how to collect the data. We then allocated 3 weeks for prototyping, and following is the data collection and validation. And then for the modeling portion of the project, this summer we computed the load and supply model, which Melissa already explained. And for fall, we plan on doing two models, an ANSYS model, which will be the heat transfer and efficiency model, and then Homer model. Our plan seeks to have everything finalized before Thanksgiving week so that we have enough time to finish any minor details. As we all know, we are in the middle of a world crisis due to COVID-19, and we took this into consideration. So 3 members of our group are going to be on campus, and 2 are going to be out of state. So this gives us the opportunity for multi-climate testing. One of our members is going to be in San Francisco, and the other is going to be in San Antonio. So we're going to have the opportunity to test our device in different cities with different climates. And obviously, we are also taking into consideration the lead time of the parts that we're going to be ordering, and that most of our work is going to be online.
Additionally, to measure the potential impact, we deduced that the following UN Sustainable Development Goals were the most applicable to our project. And to measure impacts, we will require cost analysis and energy economic modeling, which will be done later in the project after validating our thermal model and doing a cost analysis in different countries. We are also using IRIS impact analysis based on assumptions made about our potential impact. And on IRIS, we focused our impact theme on energy and energy access and set six strategic goals based on which we gained core impact metrics, examples being energy savings and greenhouse gas savings.
Thank you so much.
Thank you so much.
Answering any questions.